Good afternoon. My name is Carlos Gamarra. I'm the Assistant Director of the South Central CHP Technical Assistance Partnership. First, I would like to thank the American Institute of Chemical Engineers for having me presenting today on industrial waste heat to power applications and market trends. Okay, let's take a look at today's agenda. We will start with an overview of the CHP tabs, what we do and what we are, and continue with an overview of the waste heat to power technologies available in the market and the market potential. After that, we will continue with 4 different case studies and finish the presentation describing how to take advantage of the no-cost resources that the Department of Energy offers through the CHP tabs. CHP tab stands for Combined Heat and Power Technical Assistance Partnership. There are 10 CHP tabs throughout the United States, 10 entities created by the Department of Energy's Combined Heat and Power CHP Deployment Program. I'm the Assistant Director, as I mentioned before, of the South Central CHP tab, which covers Arkansas, Louisiana, New Mexico, Oklahoma, and Texas. In this slide, you can see the points of contact for all of the 10 CHP tabs. So please feel free to reach out to a CHP tab in your territory. We will be very happy to help you, to support you. But with what? What do the CHP tabs do? The CHP tabs support and promote the deployment of combined heat and power and waste heat to power systems throughout the United States. And how we do that? How do we do that? We do that at 3 main levels. We work with end users and associations of end users, trying to make the users more familiar with what is CHP, what's waste heat to power, and offering fact-based, non-biased engineering support. We also work with the stakeholders like regulators, utilities, and policymakers to identify and reduce the barriers to using CHP and waste heat to power. And we provide no-cost technical assistance, no-cost technical services on behalf of the Department of Energy to let end users know if waste heat to power or combined heat to power technologies are a good fit for their facilities. But today we're here to talk about waste heat to power, so let's introduce waste heat to power technologies. As you already probably know, combined heat and power recaptures heat of power generation systems, increasing the energy efficiency of the whole process by 30% and reducing greenhouse gases emissions while creating the same thermal energy and the same power as separate technologies. Combined heat and power can be defined then as the on-site simultaneous generation of 2 forms of energy, thermal energy and electricity, from a single fuel energy source. Waste heat to power is very similar, but not the same. We refer to waste heat to power as bottoming cycle CHP or indirect fire CHP. One of the main differences is that in waste heat to power, the fuel is first applied to produce useful thermal for the process, while in traditional CHP, that fuel was first applied to produce power. Waste heat in waste heat to power is utilized to produce electricity and possibly additional thermal if there is enough energy in the waste fluid. So we generate electricity and thermal energy simultaneously, but in this case there is no additional fossil fuel combustion. As you can see in the chart on the left, typically fuel is burned in an industrial process to produce heat, and the waste heat of this industrial process is recovered on a steam boiler, generating steam and producing from that steam low energy heat and power. There are different sources of waste heat. Actually, energy can be recovered from a furnace, an oven, and other industrial process and converted to electricity using a thermodynamical process, being the most common, the Rankine cycle. Engines and turbines can be used to drive compressors, pumps, and electrical generators, being a good example, a pipeline compressor station, where a gas turbine drives a compressor that moves natural gas through a pipeline. The waste heat recovered from the gas turbine can be used to generate electricity. There are other industrial processes that generate heat as a byproduct, like for example, the manufacture of fertilizers, the incineration of sewage sludge, heat release from pressure release valves, and other processes that produce heat not for a thermal purpose, but as a result of their operation. Which are the most common technologies in waste heat to power applications? Most commercially available waste heat to power technologies in the US are based on either the steam Rankine cycle or the organic Rankine cycle. The main difference is that the organic Rankine cycle uses an organic fluid in place of water and steam. This allows use of lower temperature heat sources than the steam Rankine cycle, approximately near 200 Fahrenheit or even lower. The efficiency of the cycle is much lower as a result of the lower temperature range, but this can be worthwhile because of the lower cost involved in gathering heat at this lower temperature. This technology was developed in the 1950s, so it's a pretty mature technology and low-risk technology. We also have back pressure steam turbines, pretty common in industrial applications. These turbines generate low pressure steam and power from high pressure steam with an overall efficiency of around 80%. There are also some emerging technologies like, for example, the Kalina cycle and the supercritical CO2 cycle. These are variations of the Rankine cycle that have recently entered the market. The Kalina cycle uses a combination of water and ammonia. For SRC systems, the working fluid is water, and for ORC systems, the working fluid is a hydrocarbon, hydrofluorocarbon, or ammonia. In waste heat to power applications, the capacity of steam turbines can range from 50 kilowatts to several hundreds of megawatts, while ORCs oscillate from 50 kilowatts to dozens or megawatts. So why waste heat to power? Waste heat to power is a really interesting technology because you utilize heat from existing thermal processes, which otherwise would be wasted. That's an important resource to improve energy efficiency, reduce environmental emissions, and improve the competitiveness of the US industrial sector. Probably the main technical factor to consider when you design a waste heat to power system are related with the waste heat source. Like for example, is it a gas or a liquid? Is continuous, is cyclic, or intermittent? How many operating hours a year is available? Does the temperature of the waste heat change over time? What's the flow rate? Are there any contaminants that might corrode or erode the heat recovery equipment? So characterizing the heat source, the waste heat source, is a very important step in these projects. There are different economic factors to consider when you are planning for a waste heat to power system. Being the first one, if you really want to generate power. So there are different waste heat recovery options, and the first question is, do you really want to generate power with that heat, or do you just want to use that thermal load you recover in another part of the process? Another economic factor is the cost of grid electricity, which will dictate if the savings you are going to generate are high or low, or which price are you going to be able to sell the excess power back to the grid, for example. A third factor is the cost of the integration of the waste heat to power process with your existing facilities. And the fourth factor is the availability of financial services or any kind of incentives. Okay, let's take a look at the waste heat to power markets. According to the Combined Heat and Power Installation Database, there are 105 operational waste heat to power systems with 813 megawatts of capacity installed as of June 30, 2020. In 2016, this market was estimated in 7.6 gigawatts of remaining waste heat to power technical potential in the US. The top sectors are those with large waste heat streams available for capture at temperatures conducive to generating electric power, typically industrial plants, and in the past, the bigger the better. Waste heat to power potential has been found in 48 states, being Texas, Louisiana, and California, the states with the highest potential. In this slide, you can see the potential the number of sites and potentially megawatts per state. Similar to this, same information is presented in this map. Let's take a look at the waste heat to power potential by application. In this table, you can see the number of sites and potentially megawatts per market, per application, highlighting the petroleum refining, stone, clay, glass, and primary metals as those applications with the highest potential. But waste heat to power systems manufacturers are downscaling their equipment, and that is enabling other markets to be important in this sector. Like, for example, food processing, or beverage and tobacco, lumber and wood, or even transportation. So the size doesn't matter anymore in this market. It's a matter of taking a look at your waste source and waste heat source and see if it has potential to produce electricity. Okay, let's take a look at some case studies. Let's talk about real projects. Project Snapshot 1. This is a waste heat to power and process heat located in Port Arthur, Texas. This project is going to be, there is a presentation about this specific project in the next session. So I will just say that this is a 5 megawatt system based on waste heat recovery boilers and a back pressure steam turbine installed in 2005 and saving 160,000 tons of CO2 per year. This second project Snapshot is also a project that will be presented in the next session, so I won't take too long to say that this is an oil and gas application, 65 kilowatts. This is a great example of how the manufacturers have been downscaling their equipment to fit smaller applications. The fuel is flare gas. It was installed in 2015 and enables environmental benefits such as 89% of CO2 reduction, 48% of NOx reduction, and 92% of VOCs reduction. The third project Snapshot is located in the Williams Ignacio gas plant in Durango, Colorado. This facility provides compression, dehydration, and natural gas liquids recovery and produces liquefied natural gas. In this system, the waste heat from turbines that drive centrifugal compressors is used in a steam turbine, 6.2 megawatt steam turbine, to generate 43,800 megawatt hours per year. This system was installed in 1984 and upgraded in 2014, savings almost 2,500 tons of environmental emissions per year. And the last project Snapshot we are presenting today is the Northern Border Pipeline. This project was the result of a successful collaboration among several organizations. Northern Border Pipeline supplies the land and waste heat to Ormat in exchange for a royalty on electric sales, while Ormat builds, owns, and operates the ORC plant using its power purchase agreement with the local utility Basin Electric to finance the project. Basin Electric executes a 25-year PPA with Ormat for all electricity generated in this plant. This plant is based on an organic Rankine cycle machine, 5.5 megawatts, installed in 2006, and it saves around $600,000 a year. The reductions, environmental emission reductions related to this project are 27,000 tons of CO2, 34 tons of NOx, and 124 tons of SO2. In the following slides, we're going to present a set of tools and resources that the Department of Energy has developed to help users implement their own waste heat to power projects. One of the services the CHP tabs provide is the technical assistance, and probably one of the most interesting. It's important to highlight that all these services are performed by the CHP tabs on behalf of the Department of Energy at no cost for the end user. So technical assistance starts with a screening and preliminary analysis by which we calculate which kind of waste heat to power system or combined heat to power system might be a good fit for your facilities. We also perform third-party reviews of feasibility analysis, third-party reviews of investment grade audits or engineering analysis, and we also support the end user through procurement, operations, maintenance, and commissioning processes. Other resources available from the Department of Energy is the Project Profile Database, where you will find detailed information on many different CHP and waste heat to power projects, so you can take a look at what you could develop in your facilities and what have other entities done. A very interesting resource by the EPA is the CHP Policies and Incentives database, so you can locate your own incentives in your region. For general information on combined heat and power and waste heat to power, please feel free to check the following resources: the fact sheet series and the report titled Clean Energy Solution. Two more resources, both very useful. On the right side, low cost, actually no cost, CHP screenings and other technical assistance from the CHP tabs. And on the left side, the Department of Energy's combined heat and power installation database, which includes all known CHP and waste heat to power systems in the US. You can log in and sort them by capacity, prime mover, technology, fuel, application. A very, very useful directory of CHP and waste heat to power facilities. Next steps, just check the resources available to assist in developing waste heat to power and combined heat to power projects. Please reach out to the CHP tabs, and we will be more than happy to help you with the no-cost services, with the preliminary screenings, or answering any specific question about potential waste heat to power and combined heat and power opportunities. A quick summary of this presentation: 3 main points. Waste heat to power gets the most out of waste heat flows, allowing higher overall utilization efficiencies, reducing environmental emissions and operating costs. Combined heat and power and waste heat to power can be used in different strategies, including critical infrastructure resiliency and emergency planning. They are proven technologies which have been commercially available for decades now and cover a full range of sizes and applications. So please do not hesitate to reach out to us to help you figure out if your facilities, as I mentioned before, are a good fit for these technologies. And this is all we have today. Please feel free to send any questions to my email. I will be more than happy to answer all of them. Or if you want to work with the CHP tabs, just let us know and we will be happy to work with you. Thank you very much.